Here we are, yes. Okay.
Okay, so welcome to today's seminar, and it will be by Kostas Skenderis, who is who needs almost no introduction then to the or most of the audience at least, and so he has recently been also applying, not recently I would say, for quite a while, has been applying many of the ideas of the holographic correspondence to understanding cosmology, especially the initial phase of the early universe. And he's going to tell us today about what he has been, his results on this front, and tell us about his way of understanding holographic cosmology.
Okay,
so
thank you very much. Thank you very much for the invitation to give this talk. I'd rather be there with you to give this talk in person, but clearly this period is a strange period. But at the same time, one of the effects of this strange period is that our community became more of a global community. So even sitting in our desk, we can give a talk somewhere else really far away. So I'll try to give you an overview about what holographic cosmology is, and also discuss what it has to say about the resolution of the initial singularity. So I like this to be an interactive talk, so feel free to just interrupt me with questions. I'd rather have a discussion than go through all my slides. So what I will do today is I will spend roughly half of the talk introducing the topic, what holographic cosmology is, and how you meant to think about it. And then in the second half, we will focus on a very simple model, perhaps the simplest model for the very early universe, which still seems compatible with the data, and discuss how we can use that model to understand the resolution of the initial singularity. And then we will conclude. Okay, so now let's start from the beginning. I think if there is anything that I want to come out of this talk is really this slide. So holographic cosmology, for and foremost, is a new framework. So the models I will discuss later, they maybe turn out not to be the models for the describing our own universe, or maybe have some issues of their own. But I think this is a new framework will be here to stay. So usually we think of cosmology as having Einstein gravity coupled to some matter, and then we consider a cosmological background and see how that involves. So in holographic cosmology, this piece of data now are replaced by the following two pieces of data here. So first of all, the three-dimensional quantum field theory, which is the dual quantum field theory, and that involves no gravity. And an explicit dictionary which relates observables of the three-dimensional theory to four-dimensional observables, the observables we are measuring. I also want to emphasize that in this talk, I'm always going to be discussing our own universe. It's not going to be some alternative universe, let's say with negative cosmological constant or some other features. This is meant to be a description of our own universe, and we'll also see connection with actual cosmological data. So this new framework includes all conventional models of inflation. So they are in a sense part of the parameter space of this new description. But at the same time also includes qualitatively new models that describe a non-geometric very early universe. And non-geometric here means it is a description that cannot be described as some Einstein gravity with some scalar potential of some form or another. So it's really non-geometric. So the notions of space and time, the way we perceive them today, are not valid. So this is a strongly coupled phase. But nevertheless, using holography, using this three-dimensional quantum field theory, we'll still be able to understand the physics of that phase and also make predictions about cosmological observables. So I could have given the talk describing how this framework describes conventional inflation, But actually, I will mostly focusing on these new models for two reasons. First of all, it allows us to start to build a language about what it means to have a model for the initial times of our universe when space and time still, the notions still don't make sense because you have to really combine quantum mechanics and general relativity. And secondly, as you will see, it allows us to see explicitly how to resolve the initial singularity. So here is the same comments again. So why holographic cosmology? So first of all, these models are fully consistent with quantum mechanics because you built them using quantum field theory in 3 dimensions. They are consistent also with general relativity. Actually, general relativity emerges when the quantum field theory dynamics becomes strongly interacting. And these models, moreover, are well defined when traditional general relativity breaks down, including at initial singularity, as we will see towards the end of this talk. Okay, moreover, these models are consistent with data. So here is a fit of these models to data. So here I have the CMB data. The blue dotted curve is the traditional lambda CDM fit to this data. And then the red curve is this holographic cosmology model. And as you can see, they're pretty much on top of each other. I will become more quantitative as the talks, as we move on in the talk. So in this insert, I have the low L region, and you can see around L equals 20, kind of the dip in the data. So no current description explains well the current low L data. It's about 2 sigma deviation. Now, of course, by just looking at this, we cannot see how well the 2 models do. So I have another plot where we have the so-called residuals. So here, this green region, this one over here, this represents the Planck error. This blue curve, this black curve, this one here, it's the difference between lambda CDM and holographic cosmology. And as you can see, the difference between the lambda CDM and the new model is within the error bar. So we can already see from here that they both describe the data equally well. And then we have the
Kostas, can I ask a question?
Yeah, sure.
Can you show the power spectrum, associated power spectrum? Will it
Yeah,
be
so here
or,
we have the angular power spectrum. The power spectrum is a bit boring because it's nearly flat. It looks
okay. It doesn't have any features and so on.
It doesn't have any features except that the kind of very low L's where it kind of shoots up. But I'm going to go back to that. Actually, you cannot. I'm going to describe. I'm going to discuss this a bit more later.
Okay.
Okay. Any other question? Okay. So back to this plot. The blue dots are Planck, the Planck data minus lambda CDM, and the red asterisks are the Planck data minus holographic cosmology. And you can see most of the points are again within the error bar, but of course there are some points outside. So it's not a perfect fit. Okay, so that's so holographic cosmology presents models that are, I would say, better theoretically motivated because they're definitely consistent with quantum mechanics. And as we will see, allow us to probe this region of the initial singularity, and they're also compatible with data. So what I will do today is I will give you, first I will start with an overview of holographic cosmology, try to explain more the things I highlighted in these first few slides. And then in the second part, I will discuss recent and ongoing work, in particular these 2 papers. One is PRL, which is in press, and another is a PRD, which is also in press. So this is done with people, lattice gauge theory people. So we have a collaboration between Southampton and Edinburgh. This involves one of the senior lattice gauge theorists in Southampton, and 2 senior members of the lattice group in Edinburgh, and 3 students, 1 in Southampton and 2 in Edinburgh. And this is the last part where you're using lattice gauge theory to understand the resolution of the initial singularity. Of course, this work hasn't built into a vacuum. There is a lot of work done through the years trying to understand how to apply holography in the context of cosmology, starting from the Sitter CFT papers 20 years ago by Wheaton and Strominger. Actually, Wheaton Stock was in the string conference in India in 2001. Following up by Maltasena's kind of interpretation of this as computing the wave function of the universe, which is also what we will use today. And then I have worked on this topic for over the last 10 years, starting from 2009, where we introduced the framework of holographic cosmology that we will use together with McFadden. Okay, so let me just now give you the general idea, and I'll try to be non-technical and do this first part, because some of the conceptual underpinnings are rather simple, and then many of the ideas follow from them. So I have one slide about just general features of gauge gravity duality, which are essential in what I'm going to talk later on. First of all, this is a weak, strong duality, meaning that one description is strongly coupled, the other is weakly coupled. So usually we use this in the direction that if we want to understand strongly coupled quantum field theory, then we could use weakly coupled gravity theory. So for instance, there is a lot of work to try to understand QCD-like features by looking at, let's say, QCD strong coupling, by trying to use gravity in 1 dimension higher. But here we're going to use it the other way around. So we're going to use perturbative quantum field theory in order to describe strongly coupled gravity. Secondly, there is a so-called UV-IR connection. So the UV of the quantum field theory is associated with the IR of gravity and vice versa. And again, usually this is right from the perspective UV of the quantum field theory, IR of the gravity. So if you want to understand kind of the infinities of the anomalies of the quantum field theory, you can look at the infinities in the on-shell action because of the infinite volume of space-time. I mean, that's how holographic normalization was developed. But here again, we're gonna want to look this from the opposite perspective. So if you want to understand the UV structure of gravity, then you need to look at the infrared structure of the quantum field theory. And resolving issues that come from the UV of gravity, this would be associated to resolving issues associated with the IR of the quantum field theory. Finally, in holography, of course, we have, let's say, the fundamental description, which is the quantum field theory, and then there is an additional direction which emerges, the so-called holographic direction. And this is usually associated with the energy scale that the quantum field theory probes. So let's look at that also, again, qualitatively. So quantum field theory observables depend on the scales at which we probe. So here in this cartoon is meant to describe sort of kind of, this is, you can think of it as kind of the boundary of ADS, where we have the UV of the theory. And as we go on towards the IR, there is coarse graining, and eventually the 3 apples are coarse grained, let's say 2-1. And as we move along the RG, as we move from the UV to the IR, this evolution is captured by normalization in group flow. And moreover, there is this normalization group flow is monotonic. And again, this normalization group scale corresponds to the additional dimension. So this is the way, in a sense, the story works in ADS. Now, the next slide is about how this is modified when you go to cosmology. Now, in cosmology, the dimension which is holographically constructed is time, is not space. And then cosmological evolution now corresponds to inverse renormalization group flow. So here, if we have our universe here, which is where the Big Bang is over there, where we have strongly coupled gravity. So as we move to the future, then we move to a place where gravity is weakly coupled. We know that gravity is weakly coupled in this period now. Now on the quantum field theory side, then we have an inverse renormalization group flow where the infinite past is the infrared with quantum field theory, and the UV of the theory is the future. So if one asks, what is the quantum field theory leave? The quantum field theory lives to the future.
I mean, do you expect every gravity theory to have a holographic dual? I mean,
yes, I do expect every gravity theory to have a holographic dual, but we don't know in detail how to construct. We don't know in detail the structure of the dual quantum field theory of the gravity dual. So holography originated from black hole physics as an answer to the question why black holes have an entropy that scales like the area of the horizon rather than the volume they occupy. And the answer to that question was because gravity is holographic, there is the number of degrees of freedom in quantum gravity doesn't grow like a volume, grows like an area, which is the same as local quantum field theory in one dimension less. So all gravity theories have black holes. Therefore, we expect all gravitational theories to be holographic. What we don't know is we don't know what is the exact nature of this local quantum field theory. We understand this fairly well if the space-time is ADS, and I would argue that we have enough information that the same is true pretty much also in the cosmological setup. Not on the same, exactly on the same footing, but I would say we're moving there. And this also allows us to make a connection with observations. And there are also sporadic other cases with different asymptotics, so we understand what is the dual quantum field theory. But more generally, kind of setting up the general framework of kind of the holographic description of general spacetime is a very interesting open problem, which I hope you will resolve in the medium future.
yeah, but one question is, even in the case of n equal to 4 super Yang-Mills, the dual is not gravity in general. It's a string theory.
Yes, yeah. So in this case, of course, it's going to be conventional gravity up here. It's definitely not conventional gravity down there. But on that side, I will describe it with perturbative quantum field theory. So in principle, you could say, okay, here I can have a strongly coupled sigma model. I think that's probably correct. But currently, nobody knows how to solve such strongly coupled sigma models. So this is a probably correct description, which is not so useful. So holography says there is an alternative description, which is weakly coupled, which can therefore use to solve the theory. And that's what I will be using over there.
Okay.
Kostas?
Yes.
So I have a question here. So this correspondence is could be essentially a little bit state dependent, right? In the sense that in the infrared, I mean, you may not be talking of the infrared of the vacuum of the QFT. Also, you might think of some kind of a non-trivial state here, because effectively, yes, once we go in the UV, we may not be able to distinguish, right?
Yeah, that's possible. At the same time, for the examples I will analyze, it would be the standard vacuum of the quantum field theory. Let me actually I don't have the slides here, but I have them in different docs. So let me make just a couple of general comments. First, the direction of time. We know, of course, that we perceive that there is a direction of time. So in holography, this is linked to this monotonicity of the RDF flow. Secondly, there is an issue of the kind of the entropy of the initial state. We know that because of the second law, entropy increases. But we also know that the entropy that we see today is very small compared to what it could have been. So if, let's say, the entire matter content of the universe were inside black holes, we would have a much higher entropy than what we have here. And that suggests as we go back in time, the initial state of the universe had to be very, very special, low entropic state. And that's, in a sense, an open issue to understand how could this be realized. But again, in this context of holography, all of this is completely natural because as we go to the IR, there is universality. So there is with coarse grain, so the UV has more degrees of freedom than the IR, and the description is completely universal of the IR. The different states, of course, you can have differences between different states, but if you really go to the very deep IR, you get a universal description. There are other conceptual issues.
Yes, but
yep.
But from the point of view an observer, in fact, very late time, it's as we, I mean, if you go to the very, very past, there should be some kind of overall ignorance, right? So,
yes.
One could, for an observer, it could be as good as having some kind of density matrix at very early time with finite entropy, but not zero entropy, right?
Yeah, this is true. And I think I will come back to that after I discuss the resolution of the initial singularity. And if I don't come back, ask me again to make, because it's a relevant comment, whether the resolution is actually observable for the reason you just described. Because, there is a resolution of, I mean, the theorists will be discussing naively have infrared singularities that are related to the initial singularity here. And then we will see the theories also have a built-in mechanism to resolve the singularity, which is at work. I mean, that's part of the kind of second part of the talk. And then one can ask as a second question, can you actually see this resolution in the actual cosmological data? And I would say at this point, I do not know, but there is the issue that because we haven't yet finished completely the computation which is required to see whether that resolution is visible in the data. But it is a possibility that we cannot see. So as you go to the infrared, okay, if I go back to this plot here, so this last part in the infrared is the very large angular scales. And of course, there is a huge uncertainty here because of what is called cosmic variance. So the resolution of the initial singularity is also maybe masked by the uncertainty due to the cosmic variance, which would be kind of another way to describe the fact that if we're a late universe observer, then because there is a long distance to go from here to there, then there is some intrinsic ambiguity in how accurately we can resolve the infrared singularity.
Sorry, can I ask a very naive question related to your previous comment? I mean, usually, it can happen that when you actually go through an RG flow, then in the IR, there are like multiple critical points, like multiple fixed points, like, it may not be unique, right? So I mean, in general, that's a possibility. So does that have any analog here? I mean, it's not only, so, your previous comment was about like resolving the IR completely about, let's say, one particular fixed point, but even the fixed point can be, more than one in number, right?
Let me actually say it, because this was one of the things I wanted to say. It relates to the way kind of the conventional physics change with this picture. So let me start from this side here, from the gravity. So usually the way we think of the problem is we impose some initial condition here, and then we want to evolve the data to the future. Now, if I go over here, so if I'm at some time, let's say this is the time we're discussing, then if I give the quantum field theory here, I can describe everything to its past. So if I give the UV data, then I have, in principle, all information needed in order to describe everything to the past. So in particular, if I give UV data, if I start from the theory here, there can be many UVs that arrive to this point. But if I start from here, there's only one renormalization group law. The renormalization group law is monotonic. That doesn't go in. I mean, if you go, let's say, from the top of the mountain to the valley, there is only one route. But if you're in the valley, there may be different ways to go down to the valley.
Yeah, right. I mean, RDF flows are not reversible in that way. You know, that's what you're.
Yes.
But you know, I think what I was asking is slightly different. I was asking, you know, depending on, you know, how you start flowing. Okay. Maybe it's, you know, the question is not very precise, but, you know, depending on how you start flowing or what direction you are taking away from the UV fixed point, you may end up on different IR fixed points. I mean, the IR fixed point.
Yeah. So if I start from here, as you said, depending on how I start evolving, I may arrive in different places.
Yeah.
So
does that have an analog on the gravity side? Yeah.
But if I start from my UV with, let's say, with a relevant deformation, then okay, I know how to go down, and then I can compare with observational data, and that's the approach we will be taking.
I see. You're also specifying, you know, what are the exact deformations of the, you know, that will make more or less the flow unique.
Yes. I mean, when I start from the theory, okay, that theory has, okay, the UV theory has a spectrum, and then you describe how to go away from it.
I see.
Of course, here we're not going to start from the future, because I do not yet know how to completely describe all the cosmic evolution holographically. We're only going to do this for the very early universe, and I will have here on the slide. So we're going to start with somewhere here, and we'll aim to describe the very early universe, the power spectrum that we see today.
I see. All right. Thanks a lot. Thank you.
Okay. So yeah. So now. So what is the duality? So the duality is meant to compute the wave function of the universe. So if I start again, if I put a slice here, so traditionally you would say just you give some initial conditions here that describe the evolution. So here the data on the initial slide, which I call phi, for instance, if the theory is just gravity, would be the kind of the induced metric and the explicit curvature. So the data that we give here are the sources for the dual quantum field theory. And this computes the wave function of the universe. So the sources for dual operators become the arguments of the wave function of the universe, the induced metric, the initial slice. And then if you want to compute cosmological observables, then as usual in quantum mechanics, we square the wave function, and then we multiply with the operators that compute the inner product. Now, quantum field theories, of course, the partition function can be expressed in terms of correlation functions of the theory. So the phi's that appear here also sources over there. And then you can compute the wave function of the universe by just computing correlators in the dual quantum field theory. And then we compute this, we put it here, and then we compute the observables. So this was introduced by Maltasani in 2002 in his paper on the non-Gaussianities. In the work I've done starting from 2009, we actually had we tried to build a holography being agnostic of how it's going to work, but it is fully consistent with this idea. So instead of describing the way we got into the formula that I'm going to describe in a minute, you can think of it as just using this wave function of the universe. Okay, so now using this idea, now let's go on to describe how we would describe observables. And the observables I will discuss are the ones which are actually measured. So here in this slide, I have the description of power spectra, and we also computed non-Gaussianities. So to compute the power spectra, you need to compute the two-point function of the energy momentum tensor of the dual quantum field theory. And here I give the general form, the general formula for this quantity in momentum space. So the two-point function contains two pieces. One piece, this A, is the piece which is about the transverse traceless part of the correlator. And there is a second piece, which is the trace part of that correlator. So this capital pi and the small pi is just projections to the relevant space. So now the dictionary is the following. We take these quantities here and we put it in the holographic dictionary, which is the formulas here in this box. So you compute A and B, you put it into these formulas, and then you take an analytic continuation, which I indicate over here. So you take the magnitude of the momentum, and then you continue this to the negative imaginary axis. And then if you're considering an SUN gauge theory, which is what we will be discussing in this talk, then you also need to analytically continue in a number of colors. So this N is the rank of the gauge group. Now these analytic continuations come from the way this dictionary was derived.
That's a stupid question, actually. So does it matter whether this N goes to -IN or IN here?
Yes, yeah, it does matter. So you need to have this -1, because in this way you map so in the context where you're discussing conventional slow roll inflation, these continuations are knitted so that the regularity in the interior of ADS is mapped to the Bunch-Davids vacuum. So it is, yeah, you need to have the minus in both of them, in both cases.
So, sorry, I have just a simple confusion. Is a stress tensor you are taking is not traceless?
It's not traceless. This is not conformal field theory.
I see. Okay.
And pretty much in all the talk, as you will see actually in 2 slides from now, this theory we'll discuss are never conformal. So if you would want to describe the sitter-like cosmologies, like what most people believe happen in conventional slow roll inflationary spacetime, you would need theories which are close to be conformal. But here we will be discussing theories which are non-geometric. So we're never going to be close to the sitter. So the theory is never going to be a CFT.
I see. Okay, thank you. So is it just one thing? So in 3 dimensions, this is the most general form that you can write down for stress tensor. You cannot allow for any other structure.
So in all dimensions, this is the more general form, modulo parity parity auth convolutions, which can appear in specific dimensions.
And they don't play any role. Say parity, I write down a parity auth term, that will not play any role.
They're not going to play any role in this observable. So this is the scalar power spectrum, and this is the tensor power spectrum. So if you have these additional contributions, there would be an additional component that you may want to check.
Okay.
But these are not going to play, and I'm not going to modify the formulas I give over here for the conventional scalar power spectrum and tensor power spectrum.
Okay, thank you.
And so now if you want to discuss non-Gaussianities, we have also done those. These are now linked to higher points of the energy momentum tensor. If you want, let's say, the leading by spectra, then you need to compute 3-point functions of the energy momentum tensor, and then there are similar kind of holographic formulas like this one, so then you can put them in and then get the predictions. And I will briefly describe the predictions in a few slides. Okay, so these are the formulas. Now, let me briefly describe similarities and differences between this holographic framework and more conventional inflationary framework. And let me start with inflation, which is on this slide over here. So without inflation, we know that so we are here. And this axis here is conformal time. So if we look at diametrically opposite sides of the sky, and then we see that the CMB is very much correlated. So that's what, in sense, led initially to inflation, because if I look back to the point where the CMB was created, so this line here is where the CMB was created. So then these 2 points, and without inflation, okay, this line here would be the initial singularity. So these 2 points would not have the past light cones of these 2 points do not overlap. Therefore, there was no way that these 2 points are going to know the existence of one another, and therefore that's what is left to the kind of the puzzle of the isotropy and the smoothness of CMB. So the way inflation resolves this is as, okay, let's add an additional period before that, where the space-time exponentially expands, and then these 2 points here. Now, if you go further back, then they have an overlapping region. So if the entire universe was generated there, then that's why we see a uniform and homogeneous CMB spectrum with very small fluctuations at late times. So it postulates the existence of this of the space-time. And of course, to see the to be compatible with the data, this exponential expansion has to be long enough so that every point in the sky have the time to interact. Now let's move to this side now, where it's the holographic side. So again, we are here now. This is kind of the Big Bang. Now here in holographic cosmology, we replace this part over here, which is the inflationary part, with this, what I call here, holographic phase. Now, ideally, I would want to describe all of the space-time, including that part, holographically. But currently, I don't think anyone knows how to describe this cosmological periods holographically. So for now, I'm going to settle with just obtaining the description here. So this description here, what it does is provides for me data at the Big Bang time, which are then input for subsequent evolution with Einstein equations. And that's how I get predictions today. So now, as I said in the beginning of the talk, this framework includes inflation in particular. So let's first explain how this part here is explained by this diagram over there. Now, in holography, as I described here, so if you want the power spectra, then this comes from 2-point functions. So if I'm over here, and I have these 2 points here, I want to see whether they're correlated. So the correlation, I would see the correlation by looking at the power spectrum. So here we have an energy momentum tensor inserted here, and another one inserted over there. And I want to know whether these 2 objects are correlated. Okay, and we know how they're correlated. They're correlated via the 2-point function. So let's first move to the case of inflation. So inflation, when we have inflation, this means this part of the space-time has a semi-classical description in terms of some accelerating space-time, which is close to de Sitter. Then the 2-point function of this object, one can obtain using kind of standard ADS-CFT type arguments by and is approximated by the length of the geodesic that connects these 2 points. And now you can compute this, and then this length of the geodesic is related also to how deep this goes into the space-time. So the number of foldings that we get over here is associated with how long the space-time should be semi-classical. So if the space-time is semi-classical, then this is a good approximation, and then this gives exactly the right correlators, like exactly the same correlations that we also see in the standard theory of inflation. And that's not, this is quantitative, I mean, including all 2's and pi's and sines and so on. Now, the big difference between this picture and that one is that this one still adds at some initial singularity. So inflation doesn't resolve the initial singularity. it's an effective theory that is valid only at some specific energy scales, where this site over here is meant to be an exact description, not an effective description. So here, the space-time would end only if there is an infrared singularity. So if there's no infrared singularity, then any 2 points will always be correlated by going long enough, following long enough the normalization group flow. So if the space-time is non-geometric, as in the cases I will start describing from the next slide, it's not going to be such a geometric description in terms of some geodesic in some bulk space-time, but instead would need to compute this 2-point function by doing a quantum field theory computation. And then using that result, then we have to see whether what we see today is consistent with the data we observe from satellites. Okay, so any questions on this?
I had a question. Can I ask?
Yeah, sure.
Yeah, so is your dual QFT unitary? I mean, I'm asking because in DSCFT, the CFT is known to be non-unitary. But in this case, this is just a regular unitary QFT?
You will see in the next slide what kind of quantum field theories I am discussing.
Okay.
Oops, I think I lost. Here we are. Yeah. And then you can ask me again the same question. Any other question? Okay. Okay, so models for the non-geometric universe. So the models I will be discussing are based on this Lagrangian. So this is the most general three-dimensional quantum field theory, which is consistent with the following facts. First of all, it should be perturbative. So the Fs are just some gauge fields, could be U1 or S1. Here we're going to take them, the adjoint of S1. We have a number of scalars. We have a number of fermions. We have no mass term, so it's very important these are massless. And we only have 5 to the 4 in U cavatons. Now you need these two properties in order for the theory to have a so-called generalized conformal structure. So first notice that if we're in 3 dimensions, then the Yang-Mills coupling constant is dimensional, has mass dimension 1. So this theory is never conformal because it has a dimensional parameter in its fundamental description. But this parameter is such that you can write all the terms in the Lagrangian have the same dimension. So if we assign dimensions to the fields as if we were in 4 dimensions, all of them have dimension 4. So that this lambda and the mu are all dimensionless parameters. So when this holds, then one can show that if one assigns transformation properties to the Yang-Mills coupling, as if this was a field, then this Lagrangian, this action here would be conformally invariant. But of course, that's not a symmetry of the theory. When we do transformation, the symmetry of the theory would not inform the parameters. But nevertheless, this still gives sufficient control over some of the properties that we need in order to set up the holographic universe, the holographic dictionary. So why this class of theories? So first of all, this is a class of theories which already appeared in holographic dualities. These are involved in the so-called non-conformal brane holography. And an example of such a theory is a maximally supersymmetric Yang-Mills theory in 3 dimensions. But then when we set up the holographic dictionary for these theories about, it's now 15 years ago, it was clear that the holographic dictionary was such that it holds for all theories that have this generalized conformal structure. So this is the class of theories I will be considering.
Kostas, can I ask something here? So firstly, if you have this kind of fields, aren't you saying more than the graviton, there should be an inflaton, there should be also other fields in that gravity theory?
Yeah, so the graviton corresponds to the energy momentum potential. Now, of course, this theory here, you can start writing down its spectrum. There would be some, long dimension operator, which corresponds to the Lagrangian itself is a dimension 3 operator, and this is what corresponds to the inflaton. And then, of course, there are a lot of other operators that corresponds to the other spectrum. So there would be other observables corresponding to the other operators in the theory.
So, is there some suggestion there could be some part of dark matter or something? I mean, what if you, or do you think that? I mean,
yeah. So that's a very interesting question. So, I mean, as I said here, I can only describe, so far, I'm only able to describe this, but I do hope to describe that as well. And the dark matter would be part of, so other operators over here should be part of the answer of what dark matter is. But I don't have any precise suggestion.
So another thing is that, do you think, so is it important that such theories do not have a mass cap?
It is very important they are massless, because otherwise the power spectrum would not be correct. So the fact that so this
want it
from connected with observation. So to have a nearly scale invariant power spectrum, you need the theory to be massless.
Yeah, what I mean is that you want a kind of non-trivial CFT, not a trivial infrared fixed point, but a non-trivial infrared fixed point. That's what I wanted to ask.
Well, it's not entirely clear what is the infrared fixed point, but I wanted the infrared in the region which is accessible to observational data. I want the theory to be described by this action. So this action has a dimensionful parameter. So this means its predictions differ depending on which range one is considering. So the proposal is that this type of theories are capable within the regime of validity to describe the CMB data. And I will describe that the kind of the second part of the talk, non-trivial evidence that these theories do have a non-trivial critical point where the mass is equal to 0. That's a highly non-trivial, highly non-trivial statement. But it's not clear this is kind of an infrared fixed point in the sense that this is a conformal field. This becomes a conformal field theory.
Okay, thanks, Kostas.
So sorry, I'm a little confused with your that G Yang-Mills square is mass dimension 1, whereas lambda and mu are mass dimension 0. So
yes.
You mean that the psi, the canonical dimension of phi is rather than half, it is 1, and psi is also probably 3/2, just like 4 dimension?
Exactly. So in a sense, if you write the 3-dimensional theory in terms of canonically normalized fields where the kinetic terms are standard, then of course these couplings would be dimensionful now. But now when you have the structure like I have it here, you can always rescale your fields so that the dimensionful parameter becomes an overall constant. And then the parameters that appear inside, they're dimensionless.
I see. Sorry, just in 3 dimension, mu would be dimensionless usually, and lambda will be dimensionful. Lambda would have dimension 1, but you are doing something. You are so it's not usual free theory that we are used to. It's a little different theory.
Well, I think listen, in large N theories, usually we like to kind of pull the coupling constant in front.
Yeah,
so it's not unusual from our perspective. So the fact that I can pull the dimensionful coupling constant in front and have nothing left inside is a non-trivial statement. So I'm considering only theories that have the property. In 3 dimensions, these theories are theories of this type.
Okay.
So basically you want a large N limit. That's the main point.
I also want a large N limit. Yeah, I want a large N limit, and I want to have this generalized conformal structure.
So the coupling constants lambda and mu do not run with the scale. They're just
They
like
do not run with the scale, no.
So these are always exactly marginal deformations that you have.
Yes.
I see.
Okay. Okay, so now that we have our theory, let's compute let's find what are the predictions. So first of all, when we have this structure that we've just been discussing, we have this generalized conformal structure, then one can show in generality that the form of the energy momentum tensor is fixed. So here I give only the trace part, the trace, but there is a similar discussion for the transverse traceless part. So if you look here, so this factor of n squared is because I'm going to be considering a larger limit. The factor q cubed is because the energy momentum tensor in 3 dimensions has dimension 3. That's 3. And then if this would be a CFT and T would be a generic dimension 3 operator, this F here would have been a constant. So theories with generalized conformal structure look like CFTs, except that the constants that appear in CFTs are now general functions of the effective dimensionless Stoff coupling. So in this case, the dimensionless Stoff coupling is given by this expression over here. So G Young-Mills have dimension 1, so I divide by momentum to make something which is dimensionless. And because I'm going to be considering the larger limit, I also included a factor of n. So this is the Stoff coupling. So any theories which have the structure we have just been discussing, we have a 2-point function which is of that form. So that follows from a similar argument, like the argument that says that in CFTs the 2-point function is completely fixed. Now, if one has a theory where perturbation theory is valid, so perturbation theory valid means this effective coupling is small. And you can see from here, because this effective coupling depends on Q, whether the perturbation theory is valid or not depends on which scales one is considering. So now, again, the proposal is that this type of theories are relevant in the regime where for the Qs which are relevant for cosmological observations. And then we will see in a few slides whether that's true or not. So if this G is a bit small, then this function F can be expanded in G effective. And up to 2 loops, it takes the form I indicate over here. So it starts at 1 loop. And then this F0, F1, and F2 are some constants that depend on the field content. To get a precise formula, that's a kind of a very painful computation, but okay, we've done it. So then this is the form of the 2-point function without doing any computation so far. Any specific theory, namely any theory that has specific number of vectors, specific number of scalars, and a specific number of fermions with specific lambdas and nus, would be of that form, but with now different F0, F1, and F2. So here we have a logarithm because the theory, so this theory is supernormalizable. So there's still infinities, but UV infinities. So there are UV infinities up to 2 loops. So one of the origin of the log is a UV infinity that you need to normalize, and that goes as usual. But the theory also has infrared singularities and perturbation theory, which will be the topic of the second part of the talk. And that's a second origin of this logarithmic terms. Okay, so now we computed this. Now that we computed this, now let's go and put them into the formula. So first of all, you can see here, so we need to I discussed earlier that we need to do this analytic continuation. Q goes to minus IQ and then goes to minus IN. Now you can see, so some people ask me often when I give the talks, how do you know correlators can be continued in a consistent way? Well, in this class of theories, this is very easy to answer because the form of the correlators is fixed by the underlying structure. So you can see from here the G effective. So G effective under this continuation. So you see n goes to minus IN, Q goes to minus IQ. So G effective just goes back to itself under this continuation. So this part here, nothing happens to this part. So only something happens to these pieces. And Then when we take so you can see there is an n square and a q square, and taking the imaginary part, so this takes us back to a real quantity that can be computed by just analyzing the original theory without any analytical continuation. So this is the answer for the power spectrum for this class of theory.
Kostas,
Yes.
Is this statement also, is this analytic continuation also well defined beyond the large N limit? I guess so, but just
Well,
asking to be sure.
the thing which is not clear to me is whether it's well defined non-perturbatively. I think perturbatively is perfectly well defined because this is just a series in m squared, and then you just insert signs in alternating terms. But not perturbatively, I think okay, it is not clear whether that continuation makes sense or not. So
Okay,
that's
thanks.
another open question. Okay, so now that we got our answer, then we put the perturbative answer, and then you can massage it a bit by making it more kind of cosmology, using cosmology friendly variables. Like this Q star is a so-called pivot scale in cosmology, and then one can write it in this form. So for all this class of theories, irrespectively of the specific field content and the mu and the lambda and so on, then this is a universal prediction. So now, okay, here are the universal predictions. So this should be the form of the power spectrum. There is a similar argument gives to the form of the tensors. The tensor power spectrum should be of this form. And then there are also very specific predictions about non-Gaussianity. So non-Gaussianity, there should be no local non-Gaussianity. You should have a component which is equilateral with a very specific FNL parameter, 5/36, plus a component with kind of with orthogonal shape. So if non-Gaussianity is observed, let's say you find local FNL 2 or 5, then this would rule out these theories. Or if you find that there is non-Gaussianity for collateral shape with FNL, which is 3, again, this is going to rule out this entire class of theories. Now, another way, of course, we haven't seen non-Gaussianity. They're only bounds, and these predictions here are compatible with the bounds. We haven't seen tensors, so, and again, this only imposes very mild restrictions because of the tensors, but we have seen scalars, the scalar power spectrum, and the way usually the power spectrum is discussed is via this spectral index. So now a concrete question is, if you try to fit the observational data using this or that, do the data prefer the one or the other? So, so what we did is so usually, of course, this is done in the context of lambda CDM, which is an empirical model, contains 6 parameters and 2 of them coming from the very early universe. One is the spectral index, and the other is kind of the amplitude of perturbations. And these are then traded for the parameters that appear over here. So here we have this delta naught, then there is G, which is effectively the coupling constant, and there is a beta, which is a kind of analog of running. So then what we did in the 2017 paper was to compare how well, to compare the fit of the Planck data to either this kind of the version of lambda CDM, a holographic version of the lambda CDM, where the very early universe, the power spectrum is described by that form instead of that form, versus the conventional lambda CDM, where we have the usual kind of power law. And we did this both using frequentist approach and also kind of Bayesian evidence to account for the fact that this parameterization has one more parameter than this one. And the result, okay, I show you the plot in the beginning of the talk. Let me just summarize a little bit more quantitatively the results here. So the fit data showed that this G effective is very small for all scales C and C and B, except at very low multiples. So we started by assuming we can fit the spectrum using such a quantity, but of course the best fit parameters, one has to go back and check whether with the best fit parameters, this parameter here is indeed very small or not. And it is very small, starts at something like 10 to minus 4 at the very high L's, around 2000, and becomes a further 1 when you arrive at the point of lambda around 30. So at a very low L around 30, roughly the place where this large angle anomaly appears, the theory becomes non-perturbative. So one cannot trust this perturbative description. So this was another reason why I started working with lattice gauge theories, because I wanted to understand how to describe this very low L region. Secondly, the goodness of fit for both models in the regime where both models are justified. The chi-square is given here. So holographic cosmology does slightly better than lambda CDM, but that's within 1 sigma, so there's no.
Kostas, I have a question.
Yes.
Why does it become non-perturbative at large scales? Because holography in some way, it depends on the size of the universe today.
Now you can see it from here. Look this the formula. So if Q becomes very small, then G effective becomes large. So G effective starts to become the further 1 around L equals 30.
And the spectrum arises because of fluctuations in matter fields.
Yeah, so you shouldn't really think, let's say, of the spectrum from the bulk perspective, because again, this is a non-geometric model. So you should think of it as kind of this 2-point function that I have been discussing here. So the spectrum is determined by this 2-point function and its 2-loop structure. And then you can see, so this description, the data could have immediately ruled out that description because, let's say, the chi-square is very bad, or it could have ruled out that description because after one found the best fit parameters. So we found best fit parameters for delta naught, G, and beta. And then after you have the best fit parameters, you can go and look at the scales we see in C and B, and then compute this G effective and say, is it smaller than 1 or not? And then for almost the entire spectrum, it is smaller than 1. And in a few slides, I will show you a different model where this doesn't happen. And therefore, that description was accurate, except at very low multiples. At very low multiples, the effective coupling becomes 1. And therefore, from the perspective of the confidence theory, this is a non-perturbative.
What is that about the theory that makes this non-perturbative on large scales?
Because it's supernormalizable. So supernormalizable theories always become non-perturbative at some very low scale. For the same reason they have good UV behavior, they're asymptotically free. Exactly for the same reason, they become strongly coupled in the infrared. So it's not a surprise this became strongly coupled in the infrared. What is a surprise is that the data allowed to have a perturbative description for almost the entire set of data we see in the sky.
Okay, thank you.
Okay, so now, so the fit data gave the best fit parameters. And then one can ask, are there specific models? Do this data exclude or rule in some of the models I described earlier? So this is kind of a model selection. And indeed, the data is strong enough to rule out some theories and rule in some other ones. For example, one can show that SUN theory coupled to fermions only is ruled out, is not consistent with the data. So this holographic theory should be, in a sense, purely bosonic, or I should only have a relatively few number of fermions relative to bosons. And a model that satisfies all observation constraints is SUN gauge theory coupled to a number of non-minimal scalars with a 5⁴ interaction. Non-minimal here means that the energy momentum tensor, apart from the usual terms, contains also a so-called improvement term multiplying with a new parameter. So if this new parameter would be 1/8, we'd get conformal scalars, but we're considering not conformal scalars. We're considering other values of psi. And then you can fit everything we see in the power spectrum by just choosing these 4 numbers. Actually, this lambda, what is crucial is the values of psi, this non-minimality parameter, the number of colors, and the number of scalars. Lambda can be pretty much set to any value without affecting the fit data. So the data is sensitive to 3 numbers. Okay. So this is the review of the previous stuff, and I'm already seeing I'm terribly over time. How much time do I have?
Kostas, can you take 10 more minutes or?
10 minutes.
Okay.
Okay. So I'll so what I will do is I'll try to summarize. So next we're going to move to this very simple model and discuss how to resolve the initial singularity. So I will introduce the model and give you the idea about this solution of the initial singularity, and then hopefully then I will conclude. So the model is to just throw away the gauge fields altogether and to just have a single scalar field. So this is the action, a single scalar field in the adjoint of SUN. There is one-dimensional parameter, which I will continue to call G Young-Mills, even though there's no Young-Mills in this theory, just a scalar. So the model has 3 parameters. One is lambda, one is the non-minimality parameter, and the other is the one with the gauge group. And actually, as I will argue in a minute, this lambda is irrelevant. So we really have 2 parameters. Now you can work out, you can do the perturbative computation for this theory. This is actually a much simpler computation, and okay, that's the answer. And then one can show that lambda, in this specific case, if we're in 3 dimensions, one can scale it away. So it's really 2 parameters. So we are describing the very early universe with a model that contains 2 fundamental parameters, the rank of the gauge group and this non-minimality parameter. Now it turns out that n is related to the smallness of the amplitude of primordial perturbations. So the fact that so small means the larger limit is very good. And psi is related to the tensor to scalar ratio. So the fact that we haven't seen tensor means that this parameter psi is very close to 1/8. So when you try to fit this model to data, okay, that's what you get. It looks very similar to the figure I had before, except that, okay, you can't really see it very well. There is a part here kind of shoots up around here. So this part is definitely doesn't fit very well. And again, this is the figure with the residuals. But then you can do the same exercise I described earlier to try to check for which ranges of data you have that the G effective is smaller than 1. And then one finds that in this case, actually perturbation theory breaks around L equals 260. So if I'm here in the data, so perturbation theory is valid roughly here, before I'm including that part, but not this first peak. And the model becomes non-perturbative in this region. Now, in the region where the model is perturbative, it turns out it's actually 2 sigma better than lambda CDM, a little bit than 2 sigma better. So that's already, in a sense, moves in the right direction. So if this non-perturbative region would also fit the data well, it would start to be not just competitive, but preferable than lambda CDM. But to do that, to model also this part here, we really need a non-preservative method. And that's why we turn into lattice quantum field theory. So we need lattice quantum field theory in order to model this low L region, in this case, also medium L, 260. And secondly, if we are to understand the resolution of the initial singularity, we also need to understand the behavior of the model in the infrared. Okay, so now let me quickly run through this argument. So if you have massless supernormalizable quantum field theories, these have severe infrared singularities in perturbation theory. And this was known for a very long time. And it is what I describe answering to a previous question, because the theory has good behavior in the UV. The same power counting that says that the theory is asymptotically free, exactly the same power counting says that the theory has infrared singularities. So if these infrared singularities would perceive non-perturbatively, then the theory would be non-predictive, because you can get, in a sense, no matter how small the coupling constant is, then you can get, you can change the answer due to the behavior in the IR. Now, it was argued 40 years ago that precisely the type of the theories I have been discussing, they're actually non-perturbatively infrared finite, and then the Young-Mills coupling effectively acts as an infrared regulator. So these theories have a built-in mechanism to resolve this infrared singularity, which maps to the bulk initial singularity. So the first thing we wanted to do is to verify, and here they give arguments. I mean, they conjecture that there's this mechanism, and they gave arguments. So we wanted to actually prove that the theory we have been discussing, that this mechanism is at work. Okay, now to do this, okay, what do you need to do? Okay, you need to put the theory on a lattice, you need to discretize it. Okay, that's fairly simple. And then you need to find whether a massless point exists. So one starts from a massive theory and then wants to tune the mass so that you land into a massless point. Now, once you're there, then you need to find the energy momentum tensor, which is a non-trivial exercise on a lattice. I will briefly mention why, and then compute the two-point function and then compare with data. So we're roughly here at this point. So what I will do in the next few minutes is briefly describe this part, which is related to the resolution of the initial singularity, and then briefly mention this and then go to the conclusions. Okay, this is how we discretize the model, but now let me describe that slide. So I want to simulate a theory in massless theory. So this requires introducing a bare mass and fine-tuning its value so that the theory becomes massless in the continuum limit. Now this bare mass can be computed in perturbation theory order by order and has the following features. It is UV divergent up to 2 loops, and it is infrared divergent starting from 2 loops. So the general form is given over here. So here, I use lattice as my UV regulator. So there is 1 loop divergence. Then at 2 loops, you have a log divergence, which is both UV and IR. And then from higher loops, all higher loops are IR divergent. So if it turns out that this IR divergence is there non-perturbatively, this means that the massless point doesn't exist. And the theory I have been discussing is just not a valid theory. So what we wanted to do is we wanted to see whether this massless point exists. Now the UV infinity are straightforward to deal with because it's standard minimization. One just needs to add a mass counter to them. But the IR infinities, they're either not there, or if they're there, the theory is not sensible. So if the mechanism that conjectured by these people is at play, so that essentially the IR regulator is the coupling constant, you can see here that all of these terms, all of these divergent terms, they just disappear. So what you want to do is you want to compute to check non-perturbatively whether there is critical mass, and then check whether this is the correct correct infrared behavior. And to do this, we did it using a method which is called using a so-called Bieder cumulants. The idea is fairly simple. So if you have a massive theory, if you're at a symmetric point, then you expect the expectation values of local operators to be 0. On the other hand, if you're on the broken point, then you expect the expectation values to be non-zero. So you expect to see, as you change the mass, you expect to see a behavior like a theta function. And this is a bit what you see. So kind of this lines is a small lattices, kind of the bigger lattices. As you go to the continuum limit, this just does start approaching a theta function. And yeah, this is the actual data here. You can see the bigger the lattice, kind of the closer it becomes to the theta function. We have analytic predictions for the endpoints, which are exactly satisfied by the data. And we also analyzed quantitatively whether this limit exists. And the limit does exist. And this is, yeah, I don't think I have the time to fully explain this diagram. This is an extrapolation as you go to the continuum limit. So as you move to the left, you go to the continuum limit, and this is the different data points as you go towards the continuum. There are arrow bars here, and you can see the extrapolation really goes through the arrow bars, and then you arrive at a unique value. If you start from a slightly different point, they all arrive at exactly the same point. So this is the value of the critical mass.
Kostas, the mass is simply the mass that you compute a spectrum or the first excited state or something, or?
No. This is the mass. Okay, if I go back, yeah, I went through this very quickly. So this is my action, the discretized action. This is the kinetic term, the 5 to the 4. And here I need to input some finite value so I need to find an MC so that when M goes into MC, the theory becomes massless. So this is a bare mass I need to put into my action so that when I go to the continuum limit, I simulate massless fields.
Okay, thanks. So it's here you just see there's some 2-point correlator, yes. And try to, yeah, okay.
Yes. Yeah, I think this is the slide where we argue that the theory is infrared finite. I'm not going to describe all of it, and it's a busy diagram. But what we did, we asked the following. So if you're on a lattice, so the lattice itself acts as an infrared regulator. The finite volume of the lattice is an infrared regulator. So clearly the theory one simulates on a lattice would be infrared finite because of that reason. But then one wants to understand what happens when you try to go to the continuum limit. So we defined two models, model 1 and model 2. In one case, the infrared regulator is what was conjectured 40 years ago. In the other case, the infrared regulator is just the lattice model. And then we can ask which of the two cases fit the data I described earlier, either this one's or this one's better. And there is a tool which is called Bayesian evidence to answer that question, to see which of the two models the data prefer. And here, this diagram over here gives the ranges about the significance. So I think in this diagram, you should look only at the circles. So the circles is this Bayesian evidence. So if the circle will lie within this pink region, then one would say that the data do not prefer model 1 or model 2. If they lie in this yellow region, in the upper yellow region, you would say there is a strong evidence for model 1, namely the one which is infrared finite. If it lies on the bottom yellow region, you would say the data prefer the model 2, therefore, in other words, the massless limit doesn't exist. And if it lies up here, then you would say this is decisive evidence. So just for comparison, 5 sigma would be something like around here. So discovery in particle physics would be if the circle would lie around here. And as you can see, the circles are really, really very far. So there is overwhelming evidence that this model is infrared finite. I think that's beyond doubt. So indeed, this model has a massless limit, and indeed, the precise mechanism that was proposed 40 years ago, it is at play. Okay, so that's about the resolution of the singularity. I have slides about the energy momentum tensor, which I don't think I have the time to describe. I think the main issue with the energy momentum tensor is that the lattice breaks Poincare invariance, and this means that quantum mechanically can start mixing with other operators. And in order to find the correct energy momentum tensor, which is conserved in the continuum limit, one has to resolve that mixing. And this is something that we have done. Okay, these are the slides. So now, once we found the energy momentum tensor, then we need to compute the two-point function, and that's the point we currently are. We haven't done this yet, but we have a preliminary results about a different correlator. Instead of the energy momentum tensor, just the trace phi square. That's an easier correlator to compute. So here you can see this line here is the one-loop prediction. This is the two-loop prediction. And then you can see that in the regime, so this axis here, so if we're going this direction, perturbation theory is valid. If we go that direction, the effective coupling becomes large. So in the regime where perturbation theory is valid, then the lattice point are exactly on top of the perturbative results. But then we can see that we can access this non-perturbative region where the effective coupling becomes large. So what we hope is to do the same computation for the energy momentum tensor. This would give the non-perturbative power spectrum, which we could then compare with what we get from Planck. So that's the plan. So hopefully within 2021 we'll have results. We'll see. And with lattice computations, time we need a lot of time for the supercomputer to run. Okay, so I think I'm already terribly over time. So let me conclude. So I think in the first part, I want to convince you that holography provides a unified framework for the very early universe. So in that context, conventional inflation is the case where the quantum field theory is strongly coupled. But then this new framework allows for new models where the quantum field theory is either weak coupling or has coupling of intermediate coupling, like the model, this simple model I have been discussing. So this gives rise to new non-geometric models. And in this context, the resolution of the initial singularity is related to the infrared finiteness of the quantum field theory. And in order to assess both this and also to compute the power spectrum at low Q, we need new methods. And this is what I have been building in a number of years now with lattice, using lattice methods. Such models could explain the large angular anomalies in this CMB sky, and potentially would also have observational signatures of the resolution of the singularity. Well, thank you very much for all the questions, and sorry I have been so much over time.
Thanks, Kostas. This was an absolutely fascinating talk, and it was really fascinating to hear all these new results also. So time for questions now. although we had many, we can still have a few at least. Okay, actually, I have a question related to whatever asked partly before. So, so actually, it is so nowadays we know that. Sorry. So nowadays we know, for example, that there are certain ADS, some lower dimensional ADS is conjectured to have a dual to something like ensemble of theories, right? Not only a single one. So, of course, in this context, you are not saying that, but it could be that, I mean, typically in ADS CFT, it's very hard to find an observable that can probe the singularity. And in this case, I mean, it seems that you are able to get a non-perturbative answer, and you're claiming that you would be able to compare with Planck data. But how are we sure that we have a specific quantum field theory? It could be several higher.
Yeah, so this case is not an example of quantum field theories. Now, of course, you know, when I go, if you look here, in the wave function of the universe, pass it. Yeah. Yeah, so over here, you see, we integrate. So when we do this integration, we integrate over the sources. So you could also think of this as averaging over quantum field theory, where the couplings are the sources to Gates invariant operators. So I could think of this framework as, in a sense, a similar footing as the ensemble average people are discussing, but that's only when, in a sense, we go to computing observables. So our quantum field theory is, here I had quantum field theory, which was defined. This is my quantum field theory. I do not integrate over these couplings. But in the context of cosmology, what I do integrate over is about the couplings of Gates invariant operators. I integrate over the sources that couple to Gates invariant operators. So it's not so, you know, similar, but it's also not exactly the same. So in the context of, in the recent discussion, people in a sense would integrate over these couplings. So here I'm not integrating over these couplings, but I'm integrating over the sources that couple to Gates invariant operators.
Okay, I understand. But my general question was how we sure that this exactly this okay, it's a prescription for DSCFT, but because nowadays we are not very sure about how exactly to interpret ADS-CFT in general, right? Because whether we should have if it's dual to a single theory, or sometimes it can dual to an ensemble, and so these kind of things can also spill over here, right?
Yes. I tend to be more on the conservative side. I think it is, of course, for the two-dimensional model of the JT gravity, okay, there is non-trivial evidence for this ensemble average description. But as you go to higher dimensions, I think things are far, far less clear. I would tend to be more on the cautious side, still using the original version of the theory, of the correspondence. We have one theory corresponding to one bulk. But okay, that's my personal opinion.
And such theories have a natural C function that can be related to something, some nice cosmological.
Well, I mean, the C function, yeah, they do have. Okay, you have to analyze the normalization group law of these guys. I think in the perturbation theory, this essentially the normalization group flow is driven by the fact that the coupling constant is dimensional. So it is a little bit of a trivial discussion. But in general, the C function would play an important role in cosmology, because again, the R of time now is linked to the monotonicity of the RG flow. So understanding.
Yeah, something like I was thinking like something analogous to his de Sitter entropy could be dual to, or some sort of.
Yeah, I think the Sitter entropy, or understanding the meaning of horizon and de Sitter, these are non-perturbative questions. And I think for those, one needs to understand more precisely this question of the analytic continuation, to what extent that makes sense, and under which conditions it makes sense. So these are interesting questions, but it seems to me they're still a little bit far from addressing observational issues. I would prefer first to see whether, in a sense, our universe likes these theories or not. Because if our universe doesn't like them, then okay, it still leaves them as an interesting laboratory, but it becomes a bit of a mute point. Yeah, on the other hand, if these theories completely fit all data available, and at the same time allow us to resolve issues like the initial singularity, or even lead to observational consequences, okay, then one has to understand them in far more detail than previously. And it's like similar to, let's say, Young-Mills theories from the time of the formulation by Young-Mills. It took 20 years before people really took them seriously, because they didn't know whether they make sense at the quantum level. They didn't know how to normalize them. They didn't know how they're compatible with mass or matter. But of course, once these issues were resolved, then it became clear these are part of the building block of our universe. So there would be.
Yes, since we have to end soon, so just a small technical question about this analytic continuation you are planning to do. How, I mean, using some Paddy method, or once you have the full non-perturbative answer, there should be also a way to analytically continue.
So in this case, in this specific model, it's really not any issue at all, because I have already done it non-perturbatively when I discuss it over here. Because again, G effective does nothing, so this function remains the same. And then the analytic combination of the three factors can be done exactly. So I already done it. So now I just need, now I'm computing non-perturbatively this function. So previously, earlier, I computed first this with two loops, but now I'm computing this function non-perturbatively. And I have already done the analytic combination.
Okay. In the large n limit, of course, yeah.
Yes, in the large n limit.
Then it is no problem.
It's finite.
Finite n is not.
N squared is something like 10 to the 4th in this case when you compare with data. So it's not like it's clearly very, very large in limit. So any subsequent term, would be down by 10.
Okay, I see.
Yeah. So for me, okay, from a pragmatic perspective, I don't think there is an issue there. Now, if I want to, let's say, apply this to understand what is the meaning of, let's say, the super entropy, then you need to understand better this non-perturbative effects, where in a sense the formula contains 1 over the Newton constant. So it's not perturbative.
I understand now. Okay, thanks a lot, and for this fascinating talk again. And so before I end the recording, I just request you to stay over for 5 minutes. My colleagues would also like to discuss something with you.
Sure.
Okay. So I'm ending the recording.